So just recapping from yesterday's lecture, I hope everybody can see here. So yesterday we learned about this non-relativistic reduction where for simpler case, we started with a relativistic scalar field phi and did a non-relativistic reduction, which is given by this equation here. And ended up getting an effective Lagrangian for the field psi, which is complex field and describes the non-relativistic particles. Now, today I will start with a simple example at tree level showing in some cases doing this non-relativistic reduction is tricky or can lead to wrong results. And that's where the matching is really powerful and it gives you the exact amplitude that you want in both relativistic theory and non-relativistic theory. And matching is the way how we will generally obtain the non-relativistic Lagrangian. So let me start with the simple example in the case of axion EFT. Yesterday, Professor Kaplan explained about axions. So let me write the axion EFT Lagrangian. Which is again a real scalar field phi describing the relativistic axion particle phi. Or 6 factorial by 6 by FA6. In general, the axion potential is given by some cosine type of potential, but let me say I have expanded the potential for the time being, and I have kept it up to 5⁶ term in the Lagrangian. This Fa is the axion decay constant. In general, the axion mass and the axion decay constants, as we learned yesterday, are related to pion decay constants, and there is a restriction for the QCD axion, but for axion-like particles, you can have any values as you want. So MA can be really of the order of 10⁻⁻12 or -15 eV, as small as you want. But there is a restriction from the so the lowest I think it can go up to is 10⁻23 eV or something. Okay, so the goal is I start with this Lagrangian here, and I want to end up getting an effective Lagrangian for describing non-relativistic axions. In general, the axions that form the dark matter are non-relativistic. So I want to construct a non-relativistic axion theory, which is known as NR axion EFT. The Lagrangian is just given by yeah. Also putting MA square FA. So the lambda is related to MAFA through some relation that I will have to look back. Yes. So there is a relation between this. MAFA is in pi. Yeah. But general like tidal parameters Fourier or okay. And then in general what you are writing in front of the expansion is then pi square, lambda square is 4 pi m. Yes. Times lambda. I mean, I will have to look at it. I don't have, but as I recall, there is a relation between lambda and MA and FA in some ways. Fine, then MA will be lambda. Exactly. That should be MA. That should be MA. Yeah, sorry, that should be MA. No, that's correct. So P square is equals to M square. So, yeah, so the I mean, there is this periodic symmetry. There is this, I mean, in general, the potential for the axion is some lambda raised to 4, 1 minus cosine phi by f. And this lambda raised to 4, if I remember correctly, uh, is some FA square is related to MA square. If I remember, this is my vague memory, as Seth says. And the potential is obtained by just expanding this lambda raised to 4, this cosine term. Or oh, yeah, okay, I agree. Okay. Yeah, okay. Okay. Maybe let me just check one time. Yeah, I mean, yeah, so lambda 4 and lambda raised to 6 are related to this parameter. Yeah, yeah. I just kept it separate just to demonstrate the thing. So I want to end up arriving at a Lagrangian which looks like this. This is, so the cutoff is, I'm looking at momentum scale less than MA. The axion, yeah, I mean, the hard scale is my mass of the axion. Whatever be the mass, I don't care. I'm looking at very low energy, very low axion scattering. Just like in cold atoms, you can think of like I really slowed down my atoms moving at almost at zero velocity or something. Is the point. Yeah, that MAFA square is coming because I have this format, I have this structure in the relativistic Lagrangian. I mean, in general, if I had kept everything to 1, this MAFA square business will all vanish. That's you have to work out the dimension. This is the dimension analysis you can do. You can work out the dimension, and this is the correct dimension that will give me the quantity. So the goal is to determine these parameters nu2 and nu3, which are the Wilson coefficients into my effective Lagrangian. This is the term that is obtained from subtracting the rest mass from the energy. So basically, if I have my relativistic energy as m plus p square over 2m and so on, this is the term that I have from the, basically I need to subtract my relativistic part of, from the thing. So this is the term that is coming from there. And the goal is to determine from matching coefficient, matching calculations, what is the nu2 and nu3. Sorry? Yes, yes. So you can start looking at 2-to-2 scattering as a simple example, because that's the very simplest case. So I can start doing 2-to-2 scattering. So I have in the relativistic theory, I have two axions coming in, I have two axions going out, and this vertex is just given by some minus. Yeah, just give me a minute. Yeah, so minus I 4 by Fe4. And I can do the same thing in the non-relativistic scattering. I can again look at the 2 to 2 scattering in the non-relativistic theory, where again I have the contact interactions coming from this term. Okay. And similarly, you just write the corresponding Feynman rule, which is minus I nu 2 with some factors corresponding to MAFA. If you match the two things, so okay, let me just be more careful. So mine u2 MA square FA square and FA raised to 4. So this is my non-relativistic, this is my relativistic. Okay. So I need to do when I say matching between the two, what I mean is I need to equate this to this so that I can determine what my nu2 parameter is. But in order to match the relativistic theory and the non-relativistic theory, one thing you have to keep in mind is that I started, when I did the non-relativistic reduction, I started with this root 2m factor so that I can get the correct dimensions. In the relativistic theory, this is dimensionless, whereas this has dimensions of 1 by energy or 1 by energy square. So matching here basically refers to, because I have 4 particles all together, so square root 2m raised to 4. And if you do that, this will immediately give you nu2 is lambda 4, which is all good. But now let's do the 3 to 3 scattering. Yeah, because there are 4 external states. Yeah, the 4 external states. And as you see, the simple example was there is this 1 by root 2m factor to get the correct dimensions. You can also write the dimensions of the scattering amplitude in the relativistic theory. This is dimensionless, whereas this would have certain specific dimensions. If you start looking at, for example, d sigma by d omega, which is mod f square, and this is related to some mu square P matrix, non-relativistic. This needs to have specific dimension in the non-relativistic theory, and to match the dimension, you need to divide by this. Another way this comes up is because I had this 1 by root 2m factor when I did the non-relativistic reduction. So now if I do the 3 to 3 scattering, one of the diagrams I would have is this. Another diagram I would have is this. And the third diagram I would have is something like this in the relativistic theory. So I'm doing again in the relativistic case. So this is my okay. In the non-relativistic theory, this intermediate particle is highly off-shell, which means this set of diagrams won't contribute to my non-relativistic theory and would be substituted by contact interactions. So something analogous to this. So I would only have 2 diagrams that would describe my scattering in the non-relativistic theory. Okay? I won't have the second diagram, just because if I start with, let's say, a particle at rest, then this would be carrying some energy 3m, and so it is highly off-shell. And so at the tree level, you see the number of diagrams in non-relativistic theory are already, like here it is only one less. But now if you go to higher and higher scattering, like 4 to 4 or 5 to 5, you will have like about, in 4 to 4, you would have about like 12 diagrams, but in non-relativistic theory, you would have about 5 of them or 6. And in 5 to 5, the number just keeps on increasing in the relativistic theory, whereas in non-relativistic, there would be certain finite number. Yeah. So here there is two particle scattering. This is an axion coming in, axion coming out. So let me just draw the arrow. Okay. So this is a two particle scattering, where this is a three particle all coming in like together. And that makes this highly off shell. Whereas this, as we will see, there would be a component where it would have a non-relativistic component, the IR piece of the non-relativistic piece. That would be matched onto this diagram. No, second diagram is important. So that is what it will contribute to the contact vortex. So you basically can shrink this intermediate line and join these three lines together to get a contact term. This is what is not coming up when you do the non-relativistic reductions. This is what is generally missing. So these are higher harmonics of energetic particles that are not captured just by the simple non-relativistic reduction, but they are captured in these matching calculations. Yeah. Yes. Yeah, that will capture it. So this is the point to demonstrate. This is what I'm trying to demonstrate. That when you do the matching, this type of diagrams contribute in the matching. Whereas yesterday, when I started with this non-relativistic reduction and got the effective Lagrangian, if you do the same thing in the case of with the non-relativistic reduction, you won't capture those higher harmonic terms. This is the point. So you won't capture the effect of this term, basically. If you just take your Lagrangian, so let's say you take the Lagrangian with some lambda 656 term by 6 factorial, you just do this, the term that you would get here would be different than what you get from the matching. Yes. Exactly. That's what I'm trying to demonstrate. So that's the point. Yeah. Yeah. I mean, I'm not going to calculate the three bodies cross section here. I will just do the matching calculation of the amplitude. So I was just trying to demonstrate with the d sigma by d omega here is that in the 2 to 2 scattering, like in quantum mechanics, this is related to some scattering amplitude that we saw in Daniel's talk, mod f square. And that is related to some T matrix in non-relativistic theory that defines what is the dimensional analysis for this M non-relativistic. In three-body scattering, that is more complicated. So my reason was to motivate why I have to divide by this square root of 2m factor times 4 in the 2 to 2 scattering, and then I will just use it for everything else. Like for this case, I would have to multiply by 1 by square root 2m times 6 because there are 6 external particles. But this is just to demonstrate that why we had to do it for the 2 scattering and then just use the result for the 3 to 3 scattering. I'm not doing the cross-section calculations here. Yeah. Momentum directions are important. That is the reason why we will see that this has an IR piece that has to match with this. Otherwise, your EFT is just wrong. I mean, in loop case, you see it in it's a more complicated calculation, but this is a tree level calculation where you will see that the IR term will match with IR term here. Okay. So, sorry, it will take, I'll just write down the results. So for the diagram 1, so this is my relativistic. I will just get an amplitude, which is IM1 minus I lambda 6 square by FA6, or diagram 2, this is from lambda 4, because this is from the pi 4 vertex. But as I told you, if we start with the rest mass here, let's say the momentum is 0, then I have an energy 3m, which will give me a factor here as an 8m square. Okay? Everybody clear why I got 8m square? Okay. Now, diagram 3 is something that we need to evaluate a bit more carefully. So the amplitude is 3. So you are looking at 3 to 3 scattering, where you choose 2 of them to be outgoing and 1 is 2 of them to be incoming and 1 is outgoing. So 3 to 1 combination factor, combinatorial factor from the big contraction. And then another 3 to 1 factor for the outgoing states. So this is the combinatorial factor coming from the Wick contraction, because I'm looking at 3 to 3 scattering, but in reality, there are 2 particles coming in, 1 particle going out, and then outside also the same thing is happening. Okay, so the goal is basically look at this part and expand in the non-relativistic theory, which means I write this as okay, everything is fine up to this point. This is the 3 factorial. This is 3 factorial, 2 factorial, and 1 factorial. This is coming from the fact that I am looking at 3 to 3 scattering, but I have here 2 incoming, 1 outgoing, and the other case 1 incoming and 2 outgoing. So that's the big contraction factor. So I've not done anything else except just expanded the pieces here and substituted my energy. So instead of this, I have just done m plus p square over 2m plus order 1 over m square terms or m cube terms. Yeah, p square over 2m, yes, and so on. So I did not account for the higher order terms right now, because that would lead to some derivative interactions into my theory. Okay, so I would play a little bit of trick here, because I need to expand one of the denominators. So the trick I would play here is, note that P0 is my energy of the intermediate particle, and P0 minus m is something like subtracting the rest mass energy. And therefore, I would play the trick here. I would subtract a mass and then add, and in order to simplify this particular piece. And once I do that, I immediately can do the expansion of this term, because this 2m factor is the largest factor scale into my system. So I can just expand with respect to 2m in the Taylor series. So you basically pull out the 2m factor, and rest everything is your numerator divided by 2m. Okay. And the result that one gets from this, of playing all this game and extracting out the propagator for the non-relativistic theory, is I end up getting 3 terms. So let me write the result now. Lambda 4 square, MA4 by FA4. square ME49 by 4m square. So I just do a Taylor expansion, pull out the 2m factor. This is what that 2m is, and I'm just expanding everything else in the Taylor expansion. Okay? And then so these are the three terms that I will get. Okay? Yeah. My energy, my P0 minus m is the energy of the particle after subtracting the rest mass. Momentum scales are small compared to the rest mass. So 2m is the highest scale that I have. And that is why I pull out and do the Taylor expansion, and I will get these three terms out. Okay. Now this is my IR part of the theory, because this propagator here looks exactly like the non-relativistic propagator that I will get starting with the non-relativistic Lagrangian. Okay. This, if you define as some energy E0, this will be E0 minus P square over 2m, which will, the pole is at the non-relativistic energy. This is some contact interaction term. And what is this? This has a derivative coupling. So this means I need to, in order to properly do the calculations, I would need to, if I'm doing at finite momentum or something, I would need to include another coupling into my EFT, which will be the derivative coupling accounting for like psi star, psi del square, psi dagger type of operator. But for the time being, for simplicity, we will not include the derivative coupling. You can include it and again do the matching. You will get Wilson coefficient associated with the derivative couplings. So the end, now, if I do the same thing in the non-relativistic theory, maybe I'll just write the result. Yeah. I mean, your external particles are non-relativistic to me. It cannot be large. Your in and out state are non-relativistic particle whose momentum has to be less than the rest. Yeah. Yeah. I mean, in principle, if it is large, you will account them as loss processes. And then you have to make your effective Hamiltonian to be non-Hermitian. Here, I just want to describe the real, so that would make my effective potential complex, because those high momentum particles would escape out my system. And the way we account, like I told yesterday, is you make the potential complex, non-Hermitian, and that is how you would do it. But here we assume, we consider that I'm just looking at simple 2-to-2 scattering of non-relativistic particles. So if in the non-relativistic theory, my diagram B, for example, is if you just write the non-relativistic vertex corresponding to the Feynman rules, so there is square, you would immediately get, so again, there is this combinatorial factor 3, 2, 1 square. This is the vertex part. I have already given the Feynman rule, so you can just write it. And then the propagator is just given by I times P0 minus M plus minus P square over 2M plus I epsilon. So if you look at the Lagrangian there I have a piece that is subtracting the rest mass. And you immediately see that this is the same IR part that is coming up into my full effective theory and the non-relativistic EFT. And this is wonderful, because then what we are doing is correct. The IR part is correct. And now I can also compute this diagram in non-relativistic theory, which will give me some I nu 3 factor MA square by FA4. The goal is now when I do the matching of 3 to 3 scattering, so I am 3 to 3 relativistic with square root of 2m times 6. This piece would be exactly cancelled by this piece, the IR part in the full theory, which is good. And I am left, this piece I'm not considering. I have not included my effective vertex into the effective Lagrangian. Ideally, I can include it, but so this piece is left out. So the pieces that are picked up are these. Then, for example, this and this diagram 2, where is this? This will give me the contact interactions. And the result of the contact interactions that you will get is that nu3 is lambda 6 minus 17 by 8 lambda 4 square. So what was the goal of this matching calculation? The goal was, if I would have done non-relativistic reduction, the expressions that I have written there, I would only end up getting the lambda 6 term. So this will come from non-relativistic reduction, but this won't come up in doing that simple algebraic computation. This is coming from, this term is particularly, you would have some things analogous, but this prefactor is mostly coming from the fact that there is a higher harmonic, like diagram 2, which is accounted in EFT, but not accounted in these non-relativistic reduction. Okay? So the observation is diagram 2 in full theory is absent or not accounted when just performing non-relativistic reduction. But it is accounted in the case of matching calculations. So that's the main thing. And as you keep on increasing your number of like 4 to 4 scattering or 5 to 5 scattering or 1 loop scattering, the complications are more and more higher. But this is a simple example that demonstrates how the matching has been done. Okay. Any questions? Ideally, you will have to, this is, yeah, you will have to work it out. Generally, it is not very trivial. You can include non-relativistic reduction, perform non-relativistic reduction with higher powers or higher expansions in 1 by m. Generally, this gets very tricky at some point. And so there is, yeah, in principle, yes, but it's not trivial way to go through the calculation, I would say. The matching is the more natural procedure. Okay, so yeah, so now I will, I end up with my scalar theory here for the non-relativistic theory. Yeah. Nu3. So the this one? Yeah. So this operator would be something like so psi dagger, psi del square, psi dagger psi. It will, because of this p square term, there has to be a del square derivative coming into picture. This is the point. Okay, so now I will move on to, like yesterday we discussed about how to get the Dirac spinor, or sorry, the Pauli equations from the Dirac Lagrangian. Today I will start with something called as the heavy quark EFT. So focusing on HQET calculations, trying to do some, again, tree level, not one loop business. And then if time progresses to NRQED and study like Rayleigh scattering, which is explaining why the sky is blue. So we will see how in EFT, just by one diagram, you get Rayleigh scattering out immediately. Okay, so in so the references for this is there is a HQET by Neubert. There's an archive number I kind of forget. I will maybe remind it again in the next lecture. There is heavy quark physics. This is book by Manohar and Weiss. So, yes, yeah. So yesterday there were questions that, oh, we are breaking Lorentz invariance in non-relativistic EFT. In relativistic theory, we have Lorentz invariance. Here we will see a clean example of how the Lorentz invariance is restored in some ways through something called as the reparameterization invariance. Okay, if this will give you such a clean result that certain coefficients in the heavy quark EFT will be fixed at all orders in alpha S. You don't have to do any calculation. You just do this transformation, and you will immediately find that certain coefficients are just fixed at all orders in alpha S. Some of the coefficients that are appearing in different 1 by m expansions are related. So this is such a powerful method that relates things. In non-relativistic QED, there is an analog of something called as reparameterization invariance, but it's more complicated. If somebody is interested, I can give the reference for the papers there. Okay. So the goal in heavy quark EFT is I want to describe a bound state system of a heavy quark along with the simplest system containing a single light quark or two light quarks. So either a meson or a baryon. But the meson or the baryon that I'm interested is something like the D meson or the B meson, or which is Cu bar. So for me, this is CQ bar, where Q bar is UD. There is B meson, which is B Q bar. Again, Q bar is UD. Then there are lambda C baryons, which is CQQ. Again, my Q is U and D, and something like lambda B, sigma C, sigma B, and so on. Okay. So I want to describe QCD bound state that has one heavy quark into my picture, and then it is has either one light quark, one light anti-quark, or one light or two light quarks. So why are we going into heavy quark EFT? Because this really forms the basis for non-relativistic EFTs of QCD or QED, such that NRQED or NRQCD, if you understand to some extent the heavy quark EFT Lagrangian, you can immediately get a picture of why such Lagrangians also come up in non-relativistic QED or QCD. So I have already described the physical systems that I am looking at. Now, the picture that I want to first start with is what are the good quantum numbers into my system here. So for systems like D or D star, sigma C star, the star denotes, are people familiar with this star notation? Okay. So the star denotes the spin 1 combination. I want to write what is the total quantum number. So of my hadron. So I will write it as JH. And this would be basically my heavy quark spin plus, or maybe let me write it as SL. Okay. So this is my heavy quark spin. And this is my total light spin. I do not differentiate whether there are 2 light quarks, 3 light quarks, 4 light quarks. I just want to write a total angular momentum for the total light spin. That is because what is happening is if you take the heavy quark to be infinite mass, my heavy quark is fixed and forms a static color source. So the term static means I'm taking the heavy quark mass to infinity, which means it is fixed, it cannot move. And my light quark is a soup around this heavy quark. And in QCD, you know, this soup can have several QQ bar, light quark, anti-quark pair creation. There are several gluonic interactions. So in principle, when I'm saying this is an anti-quark, it has a quantum number of anti-quark. It is really a superposition of Fock states of one anti-quark, a pair of light quark anti-quark pair, a pair of gluons. I mean, because of the non-perturbative interactions. But eventually, in the case of mesons, that superposition gives me a quantum number of the light anti-quark. In the case of baryon, the superposition of several interactions of light quark gives me a quantum number of 2 light quark pair. So because of this soup, I mean, the radius of this object is fixed by lambda QCD, 1 by lambda QCD scale. And my light degrees of freedom energy scale is lambda QCD, heavy quark, which is charm or bottom, is MQ. And in general, we see from the QCD lecture that there is a well separation of light quarks and heavy quarks. So there is like MC, MB, MT, and below there is MU, MD, MS. So all my heavy quarks are above the lambda QCD scale, and therefore this is my hierarchy. This is the scale separation that I'm always looking at. So in the axion case, the scale separation was the momentum was less than the heavy quark, the axion mass, or whatever the mass of the scalar particle is. Here, I'm looking at fluctuations. So if I go in the static limit, which is taking heavy quark to infinity, my heavy quark is fixed, but I'm looking at fluctuations which are of order lambda QCD scale, and they are much less than the heavy quark mass MQ. So what is happening here is that this total light spin, in some cases, for example, if you want to describe P wave D mesons, such as D0, D1, D2, these are called P wave D mesons, and D and D star are called S wave D mesons. P wave, as the name suggests, because there is 1 unit of angular momentum. Sometimes this total light spin also accounts for orbital angular momentum. Is everything clear? Okay. So the point is, I will show explicitly why in the heavy quark mass limit, this HQET Lagrangian has something called as the emergent heavy quark spin symmetry. But the implication is that if I take MQ tending to infinity, my SQ is a good quantum number. So SQ is conserved. J is conserved because JH, basically JH is conserved, which means my SL is also conserved. We'll see that the Lagrangian basically gives this, and this is known as the heavy quark spin symmetry. And this has profound implications for like D mesons and B mesons. This basically tells you that up to order 1 by MQ corrections, D and B are same. And this is what we also see in the experiments. Okay, and there are obviously these parity and isospin quantum numbers that you are aware of. So maybe let me just skip it, but you will probably find it in the notes. Okay. So I have already described the energy scale into my system and the physical picture, that is the soup with one heavy quark in it. So let me delve into the Lagrangian first, and then I'll come back to the heavy quark spin symmetry. Just give me a minute. Yeah. So in order to, so the main point for the construction of HQET is obviously to exploit this large mass scale. And in order to do that, what we first need to define are something called as the projectors. So I define some projector for particle. So let's say I'm in the hadron rest frame for the time being. This is my projector, and for antiparticle, this is my projector. The question is, so let me remind you what gamma 0 was. Gamma 0 was 1, 0, 0, minus 1. Okay. And this, if you do, this will give you 0, 0, 0, 1. This will give you, 1, 0, 0, 0. So why they are being called projectors? Because as you recall yesterday, I wrote my Dirac field as some psi times chi. Yes? And so if I put this projector acting on the Dirac field, I will pick up this component. Whereas if I use this projector acting on the Dirac field, I will only pick up this chi component. This is the reason why these are the projectors. There are these projector identities. They will be posted as exercise. So it's basically some simple algebra. But note that these are the expressions in the hadron rest frame. I will define what is the projector in the non-rest frame. So the thing is I want to describe the fluctuations of this heavy quark coming from the interactions of the soft gluons in this soup. So there is some gluon exchange happening with the heavy quark and the light degree of freedom. And my goal is to describe the fluctuations around this heavy quark condition. So let us define a momentum P mu for my hadron, which is basically or P mu of the, heavy quark. Let's just call it P mu. So this is the momentum of the heavy quark. V mu is the velocity of the hadron. And in the rest frame, this means 1, 0, 0, 0. So basically the idea is, let's say the hadron is moving with some velocity v mu, the heavy quark being massive, the d meson is mostly, let's say, charm, the light quark is very small. You will, as a first approximation, you will say that the velocity of the hadron is the velocity of the heavy quark. But obviously, the heavy quark is interacting with the medium, and so there are these momentum exchanges, k mu, which are coming from the soft gluons or the soft light quarks into my theory. So really, k mu in some sense is order lambda QCD for me. Or yeah, basically in more concrete sense, this is lambda QCD square. And starting with this momentum, let me first start writing the heavy quark propagator, because that will give me the idea on what is happening here. Yeah, so since I defined the velocity, so now the projectors in terms of velocity are given by p particle, which is 1 plus v slash by 2. P antiparticle is 1 minus v slash by 2. Whereas here I had defined in the hadron rest frame, so this is just simple. So let me write the heavy quark propagator. So basically, in simple terms, the Dirac propagator is given by IP slash minus M plus I epsilon naught, which is and then I just use this expansion here into this. So by doing this, what I'm saying is that I'm basically the k mu are describing the fluctuations of the heavy quark because of the degrees of freedom, because of the interactions with the soft degrees of freedom. And so I end up getting so basically what I'm doing is I'm describing my heavy quark, which is moving with momentum p, as this propagator in the Dirac theory. Then I'm just using this expansion, removing out the piece related to the rest mass, and what I have is something like a propagator describing the fluctuations of the heavy quark. In the anti-quark case, if I have to describe heavy anti-quark, this is just for your knowledge. So the reason I'm talking about heavy anti-quark, because as I mentioned, this is the piece that projects onto heavy particle or heavy quark. In the case of heavy anti-quark, so my propagator will be some I minus P slash minus M plus I epsilon naught. If I just do the similar expansion, what I will end up getting is 1 minus V slash by 2 I by, I think, minus V dot K plus I epsilon naught. This is left as an exercise, so you can just do it. But the point is, you have to start with minus P slash because the particle propagation is opposite to the current. And this immediately, obviously, this is order 1 by M expansion that I'm ignoring. You can do the similar thing for the vertex. I'll just finish this and then we can take a break. So we can just do with the heavy quark gluon vertex. where if you do the same thing, so I have this vertex, which is described by minus I G T A gamma mu. If you use, yeah, so the corresponding thing in the HQET will give you something like, yeah. Yes. Instead of gamma mu, you get a substitution with V mu, describing the interactions of the heavy quark EFT. So in order to get that, you start writing this, thinking that this is some internal propagator. You write the propagator here, you write the propagator here, sandwiched this vertex in between the two propagators, expand the momentum, and you get this. So this in order to get this propagator and in order to get this vertex, the Lagrangian that one needs to write is A plus light quark, where D is my covariant derivative. D is del mu minus IgA mu. Okay, all clear? And you see, if I expand this, the vertex that I will get is this one with the V mu vertex out. And the H nu field is my P plus or P particle acting on the Dirac field that I have called as psi earlier. Okay, so sorry to change the notation. And it satisfies also the relation that 1 plus V slash by 2 H nu is H nu. So so I use the notation V because we are separating, we are saying that there is a velocity V mu that is kind of labeling my one particle state or the heavy quark's degree of freedom. This is equivalent to the psi field that I had introduced earlier. So just to make the notation clear. And this satisfies this projector relation. You can use the definition of the projector and confirm this. This is, you can see it as an exercise. So, okay, so I will, I will stop here for the lunch, and then we will try to get to higher order term expansion in HQET Lagrangian, so getting 1 over m terms in HQET Lagrangian. Remember that yesterday I mentioned that there is this 2m factor in the Pauli equation that comes up, and you will see that 2m factor also appearing here, and what is the physical meaning that is basically associated with that 2m. So we'll meet after lunch. Thank you.